Hello, this is Carol. Welcome to my fifth mini presentation. In this presentation, I'm going to navigate through Koch snowflake. This is the outline for this presentation. I will start from what is Koch snowflake and move on to who is Helge von Koch. And then I will be talking about the formation of Koch snowflake briefly. And I will conclude with some applications of Koch snowflakes and fractals. So, what is Koch snowflake? It is one of the most famous and the earliest fractals. A fractal is a never-ending pattern which shows self-similarity at increasingly smaller scales. Koch snowflake is also known as Koch curve, Koch star, and Koch island. It was discovered by the Swedish mathematician Koch in his 1904 paper on a continuous curve without tangents, constructible from elementary geometry. A Koch snowflake is built up by iterations, which means it is built through repetition or in a sequence of stages. Let's take a look at who Niels Fabian Helge von Koch is. He was born in a family of Swedish nobility in 1870. He went to Stockholm University for his math education and later became a professor of pure mathematics until his death in 1924. Throughout his career, Koch published several important papers on number theory, especially on prime number theorem. However, he was most famous for Koch snowflake, for its being a continuous curve without a tangent. It was a big news in the mathematical circle when it came out. How is a Koch snowflake formed? First, we can start from an equilateral triangle. And then we can divide each line segment into three smaller segments of the same length. We then use the new length to draw newer equilateral triangles, as we can see from the second image here. 1, 2, and 3. These are our newer and smaller equilateral triangles. And as we move on, you can see that for this one, we have newer and smaller equilateral triangles. So the process can be repeated infinitely. Let's take a look at the animation of Koch snowflake. As we can see from here, as the process continues, the perimeter becomes more complicated. As we zoom in, we can still see numerous tiny equilaterals around the perimeter. They are self-similar. As we zoom out, you can see that the shape looks like a snowflake. Okay, let's take a closer look at some geometric properties of Koch snowflake. Let's think about the length. First of all, we're going to call the original equilateral triangle as the seed, which has 3 edges, and the length of each edge is 1 unit long. So the length of the curve, or the perimeter, is 3. As we move from seed to step number 1, you can see from the table, the number of edges would become 4 times. But the length of each edge would become 1/3. So the length of the new curve would be 4. So as you can see from here, from the table, the curve can actually grow infinitely with a factor of 4 over 3. How about the area of Koch snowflake? So as we can see here, we have our original, the seed triangle. First, we're going to divide the triangle into 9 smaller pieces. And as you can see from the table, when we move from the seed to step number 1, as you can see from the visual representation here. So for the new step, there are 3 newer triangles emerge, and the area of each new triangle would be 1/9 of the seed triangle. So we're talking about this one, and this one. So you can see that the added area would be 1/3, and the total area would be 1 and 1/3 in step number 1. As it continues, you will see that even though we have more and more new triangles, the area of each new triangle gets smaller and smaller. So the added area gets smaller as well. The total area gets closer and closer to 1.6. In other words, there is a limit to the area of the curve. Whereas, if we compare it to the previous table, there's no limit to the perimeter. So how can Koch snowflake or fractals be applied in daily life? Among many applications in progress, I was intrigued by one discussion in a math YouTube channel, 3 Blue 1 Brown. In this particular discussion, the host, Grant Anderson, proposed that the real definition for fractals is not self-similarity or continuous functions, but as a new way to define dimensionality. So in the video, he used the roughness of coastline around Britain and Norway. From this image, we can see that the coastline around Norway is actually rougher than its British counterpart, as you can see from the numerical information about their dimensions. The title of this YouTube discussion is Fractals Are Typically Not Self-Similar. I highly recommend everyone to take a look at this video and also the channel itself, because when I was watching the video and other videos on this channel, I was really surprised by the beauty of mathematics through computer science, especially through animation. It just makes understanding math more intuitive. So, at the end of this discussion, Anderson used 2 different dimensionalities. As you can see from here, one of the relatively peaceful surface, and you can see that the dimension is about 2.5. And the other is of the sea in the storm. You can see the change of dimension. It becomes about 2.3. He concluded that fractals can actually change how we think about dimensions. In other words, we are not limited to 1 dimension, 2 dimensions, 3 dimensions, or even 4 dimensions. We should actually look at dimensions at smaller scales. And fractals change the way we look at the world as well. Fractals, and of course Koch snowflake, exist everywhere in the nature. And such natural existence, I would argue, is worth exploring further and further. So here comes to the end of my presentation. These are my image references. And these are my references in general. Thank you for listening. I'll see you next time.